Hello guys. So today we're going to talk about how we deal with what are called continuous random variables. Alright, so height is going to be our paradigmatic, continuous random variable. What we've dealt with so far in the past have been discrete random variables. So for example, if you were to play the lottery, right, I'm just going to put LOT here. If you were to play the lottery, you could win $0, you could win $10, $20, or $30. We'll say that's a hypothetical lottery ticket, and these are the four different possible outcomes. All right, now notice you can't win $5, you can't win $2. Those aren't possible options. It's only $0, $10, $20, or $30. With height, it's going to be very different. All right. So, what's interesting with height is, let's say some men are, around 68 inches, all right, whereas other men are around, we'll say, 71 inches. In between these two heights, there's an infinite variety of different heights. All right, not only could you be 69 inches tall or 70 inches tall, but you could be 68.1 inches tall. You could be 68.001 inches tall. You could be 68.2378964 inches tall, and so on. So there's an infinite variety of different heights that are in between being 68 inches tall exactly and being 71 inches tall exactly. All right, now that's going to cause certain problems. So when we're dealing with our discrete random variable, I'll write discrete right here to differentiate. All right, when we're dealing with our discrete random variables, for a given value, there's a definite probability. So here what we're saying is, if you buy this lottery ticket, there's a 30% chance that you win $10 exactly. There's a 20% chance that you win $20 exactly. Not so with these heights, all right? The probability, all right, if I yank a person off the street and measure their height, the probability that that male will be 68 inches exactly, not 68.1 inches, or 68.0001 inches, or 68.23745 inches tall, but 68 inches tall exactly, that probability is going to be 0. All right, and so what do we do? Like, if the probability of any specific height is always 0, the probability of any specific value on a continuous random variable like height, it's always 0. It's always vanishingly small, and we just put 0. All right. Technically, we would say it approaches 0 as its limit. All right. Well, remember that there's other kinds of probabilities that we can calculate with this discrete random variable. We could also calculate the probability of winning, we'll say the probability of winning any money at all. What's the probability of winning money here? Which in this case is going to be something greater than or equal to 10 bucks. All right, so we could calculate that. The way we would do that again is we would add 0.3, so 30% chance of winning $10, a 20% chance of winning $20, and a 10% chance of winning $30. So all of those are winning $10 or more. So we just add those probabilities up, and we say there's a 0.6 or 60% probability of winning at least $10. Now we can do something similar to that, thankfully, when we are dealing with continuous random variables. And let me show you how we can do that. Now I'm going to start not with this one because this is still this is still too complicated for my taste. Let's do something a little bit simpler. I'm going to go ahead and delete this. Put my head over here. All right, so let's go ahead and consider this scenario. All right, it says Jaden takes the same bus to work every morning. The amount of time, y, all right, that's our variable, y, the amount of time in minutes that he has to wait for the bus to arrive on a randomly selected workday morning is described by the density curve that follows. So we had this density curve before, and that's going to be a little bit problematic. Let's make it a little bit easier. So instead of having that, let's say that here is our density curve. All right, and I guess I'll actually do it like this. All right, so Jaden has to wait anywhere between 0 minutes, all right, and 0 seconds, no time at all, and 10 minutes. Now notice that the height on this density curve is constant. It doesn't go up and down, all right, it's constant throughout. Our density curve over here, and these are called density curves, by the way, we can see that people that are around 71 inches, people around that height are the most common type of height you'll come across. Less common would be those who are around 68 inches. All right. Less common still are those around 65 inches, and so on. Also fairly uncommon would be humans that are around 76 inches tall. All right, and what would that be? That would be like 6'4.5", relatively uncommon for a male. But what's fairly common for a male is being about 71 inches. That's what's most common, being around that area. Now here it's different. All right, this height is consistent, which means that the probability that Jaden has to wait about 0 minutes, that probability is the exact same. That happens just as often as it does that he has to wait 10 minutes, which also happens just as frequently, or has the same probability as having to wait, we'll say, 5 minutes, and so on. Any specific time period between 0 and 10 minutes is equally likely. All right. Now, here's the way this is going to work. Let's say we want to find, so remember over here I could find the probability that the person wins more than $10. All right, for that interval. Likewise, I could find the probability that Jaden has to wait between 0 and 2 minutes. I can find that probability. The probability that he has to wait 2 minutes exactly, again, that probability is going to be 0. All right, because maybe he waits 2 minutes and 1 second, or 2 minutes and a nanosecond, etc. So the probability of a specific time is going to be vanishingly small. But if I were to do it for an interval, that's actually fine. And so the way to think about this, all right, is he's going to have to wait somewhere in this interval between 0 and 2 minutes. So I'm going to shade in this interval right here. All right, so he's going to wait somewhere in that interval. Now the area of this entire thing, not just this shaded portion, but this entire rectangle, that whole area must be 1. Okay, that whole area must be 1, or in other words, it must be 100%. All right, so if this whole area must be 1, and the length of it is 10, then the height of it has to be 1 over 10. All right, because 10 times 1 over 10, that's just going to be equal to 1.0, or 100%. Now, if the height is equal to 1 over 10, then what's the area of this shaded portion? Well, what's the length? The length of this shaded portion, all right, it's 2, all right? So the length is 2. The height, we just said, is 110. So if we multiply 2 times 110, what we're going to get is 2 over 10. And if you put that in your calculator, that's going to come out as 0.2. So in other words, there's a 20% chance that Jaden has to wait between 0 and 2 minutes. All right, let's try a slightly different one. All right, so what's going to be the probability that Jaden has to wait between 3.5 minutes and between 3.5 to 6 minutes? All right, so 3 minutes and 30 seconds to 6 minutes. What's that probability going to be? All right, well, what's our length and time, this time frame? Well, from 3.5 minutes to 6 minutes, that's going to have a length of 2.5. All right. So in other words, like where would 3.5 be? It would be like somewhere like right here. All right, that's going to be a decent estimate of 3.5. And 6 is going to be like right here. All right, and so that this length is going to be equal to 2.5. And you could also get that just by subtracting 3.5 from 6. So that's our length, and we're going to multiply that by our height one more time, which is 1 over 10. All right, and if you put that in your calculator, here's what it's going to tell you. It's going to tell you that's going to be equal to 0.25. All right, so there's a 20% chance that Jaden has to wait between 0 and 2 minutes for the bus to arrive. But there's a 25% chance that Jaden has to wait between 3.5 minutes and 6 minutes for the bus to arrive. All right, and again, the idea is, so here's, I guess I haven't stated this yet. All right, if the area under this whole rectangle has to add up to 1, and that's always going to be true, we want to know what percent of this rectangle are we talking about. So if we're looking at this area, all right, this part where we're waiting 3.5 to 6 minutes, all right, that's going to take up this much space. All right, and what percent of this rectangle as a whole is this blue rectangle I've shaded in? That's 25% of this whole area of this rectangle is included right here. All right, so let me show you really quick how this applies over here. So let's say I want to know the probability that somebody is between 68 inches and 73.6 inches. All right, let me shade in the area because I'm running out of time. So I've shaded in this area under the curve between 68 and 73.6 inches And we'll say that that's about 68% of this entire area.